It's time to start doing inference with our hidden Markov model. So we figured out how to set up a hidden Markov model for that occasionally dishonest casino example, which looked like this. At every step, the dealer has either a fair or a loaded coin. The dealer flips, we see the coin flips, but we do not know which coin the dealer is using because the dealer can switch between the coins with sleight of hand so that it's invisible to us. And we would like to infer, given what we can see, given the emissions, the heads and tails, we want to infer the most likely steps where the dealer was using the fair coin versus the loaded coin. Okay, there are many possible assignments here, right? Many possible ways to say that the dealer was using fair or loaded at each step. If we have k steps, for example, if our emission string is length k, then we have, in this example, 2 to the k possible paths to explore, possible sequences of states. That's a lot, but we really just care about one, right? We care about the one that maximizes the probability, which is the most likely. And so we use P star to denote this special path, the one that is the most likely, given the emission sequence. And one way to define the problem we're trying to solve is like this. P star equals the argmax over all possible choices of path P of probability of P given X. Okay, so let's just look at all the components here. This is an argmax, so as opposed to a max, right? A max would give back what is the maximum probability. We care which is the path that gives the maximum probability. So that's a argmax rather than a max. This argmax is over all possible paths, so we have P down here. And then this is the probability of something that is free, right? The path is not known to us. We're trying to optimize for it. It's our optimization variable. But given something that we do know, right? This is just the emission string. This is given, this is known. So of all possible paths, which is the one that maximizes the probability of the path given the emission? Now we can use Bayes' rule to rewrite this conditional probability. If we do use Bayes' rule, then we would get probability P comma X, so the probability of the joint probability of the path and the emission over the probability of the emission. Okay, so we could have written it this way too. This is just definition of what is a conditional probability. However, notice something about this fraction, and in particular about the denominator, which is the denominator is the probability of an emission, and that's fixed. So this is just some probability. That probability does not vary with choice of P, right? So the denominator would just always be the same. And since we're computing an argmax here, right, we're trying to figure out which is the P that maximizes this. Well, we don't need the denominator, right? If we simply omit the denominator, that's going to give the exact same answer than if we included that compared to if we had included the denominator. So let's just omit it. And if we omit it, what we see is that computing what we originally said we wanted to compute is really just the same thing as computing the path that maximizes the joint probability of the path and the emission sequence. This is the mathematical problem we would like to solve. When we solve this problem, we say we are doing decoding. So given the emission string, what's the most likely path? That's a decoding problem. Okay, how do we solve it? Is it easy or is it hard? Okay, well, one thing we know how to do is to compute joint probabilities. That's easy, right? Because a joint probability is just a product of many conditional probabilities and a marginal. If we have computed a partial joint probability, such as the joint probability just over 1, 2, and 3, so P1, P2, P3, X1, X2, X3, if we've already computed that, and we would now like to compute a larger joint probability, this time over the first 4 steps, well, that's easy. We can just take the solution from the first joint probability, the one over the first 3 steps, and we just have to multiply in 2 more conditional probabilities, right? This one here, this transition probability, and this emission probability. Oh, so that's very easy, I would say. Now, that's not our situation now. Our situation now is that P is not known, and we're trying to find the P that maximizes the joint probability. So we would like to know the argmax of P1, P2, P3 over this probability. Let's say that we knew that for a moment. Would it be easy from that to compute this larger argmax over P1, P2, P3, P4? Okay, the answer is sort of. Not quite yes, not quite no. It is more complicated than the joint probability, but still doable. Not much more complicated. Okay, why is it more complicated than the joint probability? Well, let me show you an example that makes this clear. Here's our, our favorite occasionally dishonest casino example. I had to change one small thing here, which is this probability right here, just to make it so that this works for a small example. And so the dealer is somewhat less likely to switch coins in this version. And if we have this as our emission string, heads, tails, tails, heads, heads, if that's what we saw the dealer do, then the argmax P, the path that maximizes the joint probability of the path in this emission, is this one, all fair. Fair, 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 fair. Right? So the dealer was using the fair coin in each step. If the emission string is one coin flip longer, and that additional coin flip is a heads, so now our emission string is heads, tails, tails, heads, 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 then you might think that the new argmax P, right, our length 6 path that maximizes the joint probability of the path and the emission, would be like F, 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 and then one more, right? So F, 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 or F, 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 L. You might think it would be one of those, but it's not. It's all L's. And in both these cases, it's not a tie, right? That 5 Fs, that's the best path, and it's not a tie. It's not tied with anything else. In the second case, those 6 Ls, that's the best path. It's not tied with anything else. So extending the emission string by 1 does not similarly extend the path by 1, right? It's not quite that easy. Changing the emission string by 1 extra letter could have ripple effects backwards through the path that we choose. So it's not going to be quite as simple as adding one more letter onto the path that we've computed so far. But on the other hand, it's not that much more complicated because we can just bring in one more insight here. All right, so let's again think about the smaller problem, which in this case is the problem over 5, a prefix of length 5 of our emission string. H, T, T, H, H, heads, tails, tails, heads, heads. We can consider two different argmaxes. We can consider the argmax over all possible paths, matched up with this emission string, ending in fair. Right, that's what we have up here. This is all possible paths. P1 is free, P2 is free, P3 is free, P4 is free. Those are all free to be either fair or loaded. But we are insisting that P5 be fair. So we're just computing all possible paths, except we're requiring that the fifth one, the fifth state in the path, be fair. Well, of all those, the one that maximizes the probability is this one, FFFFF. That happens to also be the one that maximizes the overall probability, as we saw before. However, we can also compute the argmax path, insisting that it end in L. So, in other words, P1, P2, P3, and P4 are free, but P5 has to be L. And so over all of those paths, which one maximizes the joint probability of those paths and the emission string? Well, it's this one here, 5 Ls. Okay. So if we insist that the final state has to be fair, we get this as our argmax P. If we insist that the final state has to be loaded, we get this as our argmax P. And the point that I want to make here is if we now ask about an emission string that's one flip longer, we are extending one of these two. So whatever our answer is for the length 6 emission string, it has to be an extension of one of the length 5 emission strings, as long as we've computed a separate one for each possible ending state. Okay? So our answer will have to be an extension of one of these. So we still have work to do, but the good news is the work just requires that we take the maximum or the argmax over a number of possible extensions equal to the number of possible states. Okay. So this formulation that we're talking about here, that we're using, is just another instance of our favorite algorithmic design strategy for problems that have optimal substructure. So for problems that have optimal substructure like this one, we like to use dynamic programming. So we'll think of how we are proceeding in this computation as though we're filling in a dynamic programming table or matrix. So the matrix is pictured on the screen now. There are two rows to the matrix. This one, when we're considering solutions that end in the loaded state, and this one for when we're considering solutions that end in the fair state. And when we fill in one element of this matrix, what we're filling in is like a partial maximum joint probability. It's like a maximum joint probability over a prefix of the emission string corresponding to which column we're in, and all possible paths ending in L if we're up here, or all possible paths ending in F if we're down here. Okay, so that's what we fill in each of these states. So just as a little quiz to see if we understood that, okay, what would go in that element there? Okay, well, it would be whatever maximizes, so let's write this down. Whatever maximizes all possible length 4 paths ending in F, right? So over all possible length 4 paths ending in F, and I'm going to write that this way for now, XXXF. Just imagine X is some state, either F or L. So the max over all possible state sequences, state F, comma, the length 4 prefix of the emission string, which is heads, heads, tails, tails. So that's what would go there. It would be the maximum over the probability of all possible paths ending in F of that path, comma, HHTT. Likewise, what would go here? Okay, similar story. It would be the max over all possible paths ending in L. And I think there's 1, 2, 3, 4, 5, 6, 7 X's here, followed by L, comma, the emission string up to and including that column. So it's going to be heads, heads, tails, tails, heads, tails, heads, heads. Oop. There we go. Okay. So that's what's going to go. Likewise, that's what's going to go in each of the elements of our dynamic programming matrix. And so we're going to fill it in left to right. And we're going to fill it in this direction. So starting with the smaller products and then moving on to larger and larger ones. Okay. When we go to fill in one element of this table, we are going to need to use a maximum, right? Because there are multiple possibilities for what the previous state is that we should pick in order to maximize the partial joint probability up to this point. So if we're in step I, there's a question about what's the best state we could have been in state I minus 1 in order to maximize the value that we fill in for step I. And so the partial maximal probability is going to be a function that looks like this. So let's say we're thinking about loaded comma I. So the state loaded comma I. Well, okay, and let's say the corresponding emissions is heads. We need to multiply in the emission probability, which is dictated by the fact that the emission at this step is heads, and we are considering at this time the loaded row of the dynamic programming matrix, so we have to put in heads given loaded. Okay, times the maximum of one of two choices. Either we were loaded in the previous step or we were fair in the previous step. Those two different possibilities give us two different transition probabilities that we should consider. So we need to look up both what is the S, which is to say what is the partial maximum probability up to that previous step for that choice of fair or loaded, times what is the transition probability, right? We're currently considering loaded in step I. So it's going to be loaded given fair or loaded given loaded, depending on, depending on the term of the maximum. Okay, and this is a more visual way of picturing that. We're trying to compute this partial maximum joint probability here. All right, so we have our emission probability down here. We always have to multiply that in order to get this probability. But then we also have to take the max of two possibilities. One is that we were loaded in the previous step, and then therefore the transition that we conducted was loaded to loaded. So we have to multiply in that probability. Or we were in fair in the previous step, and so we have to multiply in loaded given fair. Okay, so this is what it would look like if we were filling in an element in the loaded row. If we were filling in an element in the fair row, it would look like this. Okay. The main point being we have this maximum, which is the maximum over all possible states we could have been in the previous step. Okay, let's put it all together and let's actually fill in some elements of a real Viterbi. This algorithm is called Viterbi now that we're using to do decoding. This dynamic programming algorithm is called Viterbi. So let's do the first few steps of this Viterbi algorithm. Okay, let's do our favorite occasionally dishonest casino formulation. And let's start in the very first column here. First column is special because we are starting out, which means we're going to use our initial probabilities to fill in the first column. Either we start fair or we start loaded. There's a 50-50 chance. So this is going to be, if we want to fill in this element here, that's going to be probability loaded times probability of heads is in the first position. So probability of heads given loaded. This is going to be probability of fair times probability of heads given fair. Okay, there they are. Probability loaded, probability heads. Those are both 0.5 over here. These are both 0.5. Probability heads given loaded, that's 0.8 because it's the loaded coin, so it's higher than 0.5. Probability of heads given fair, that's just 0.5. Multiply those two things out. You get for the loaded row, you get 0.4. For the fair row, you get 0.25. Okay, so far so good. We filled in one column. Now let's move on to the next column, and this is where it gets interesting because first of all, I drops away. We don't need the initial probabilities anymore. We already handled that. But now we need to do these maximums in order to compute the partial joint probabilities up to these different states. Okay, so let's focus on this sort of orange highlighted cell here. That's what we're calling S sub L comma 1. So what do we need to multiply together here? Well, first let's multiply in the emission probability. Heads is our emission for this step, and we're in the loaded state. So we need to start with probability of heads given loaded. Given loaded. Okay, so that'll get multiplied in. And now for the maximum, right? We need to take the maximum over two possibilities. One is that we were in the loaded step previously. And so what we have to multiply together here is whatever we find here, right? Whatever value is in that cell. So let's just go ahead and write it in 0.4 times the transition probability, in this case of loaded to loaded. And so the second choice would be that we were fair in the previous step. That's 0.25 probability loaded given fair. Okay, let's clean this up. And let's plug in the numbers. And we end up getting as our answer 0.19. There's actually more after the second decimal place, but I'm leaving that out. So 0.19, that's better than if we'd chosen, for example, this second. That was this, right? So 0.19 came from the choice where we were loaded in the previous step. If we had chosen fair in the previous step, we would have had to multiply 0.8 times 0.25 times 0.4. That's 0.08. So that did not win the maximum. That was not the maximum of the two choices. The maximum of the two choices came from the loaded to loaded transition. And we plugged in the 0.19 right here. Again, the transition that quote unquote won that was maximal, that won the maximum, was loaded to loaded in this case. Okay, let's keep going. Let's do this orange highlighted guy. I actually filled most of it in already. So this is the fair row. So first we need to do probability of heads given fair. That's the emission probability. Then we need to take the maximum of the two possible choices of the previous coin flip, the previous state. So for loaded, that's 0.4 times probability of fair given loaded. And then for fair, that's 0.25 times probability of fair given fair. Multiply that out. We end up with 0.08. That comes from the first choice again. So that comes from the fair given loaded transition. This transition. Okay, that's what won our maximum. This other choice is a little bit lower. I think these come out to, this first one is 0.08. Oop, that's an 8, 0.08. And this second one comes out to 0.075. So the first one wins. So loaded, fair given loaded is what wins. Okay? Etc. We can fill in the whole matrix this way. At each step, we can keep track of which was the previous state that won the maximum. And if we do all this, we end up with a filled in matrix. I left out most of the numbers, but I showed you the numbers for the final column here. This is, again, based on that same example we were just working. And if we kept track of all the arrows as we went, then we kept track of what allows us, every dynamic programming algorithm ends with a traceback step, right? You want to go backwards from what seems to be the best solution in order to figure out how did you get there. And so if we fill in this whole matrix, we want to first of all look in the final column of that matrix and figure out where's the maximum probability, because that tells us what the final state is in our decoding. In this case, the loaded state has the higher probability. All right. So okay, so just you have to look at the exponents, right, of the fractions, right? This one's larger because the exponent is 10 to the minus 5. This is 10 to the minus 6. So that top one is the larger probability. So we would start there and we would trace back, which is to say, okay, well, we're loaded here. And to get here, we went loaded to loaded. So we were loaded in the previous step too. And to get here, we went loaded to loaded. So we were loaded in the previous step, loaded in the previous step, again loaded in the previous step. Here, we transitioned from fair. So we were fair in this step. And here, this was fair to fair. So we were fair in this step. Here, also fair. Here, also fair. To get here, we came from loaded. So we were loaded in this step. Loaded in this step. Okay, so I kept going backwards through the matrix asking, how did I get here? Which was the term of the maximum that provided the actual maximum probability? And although it's a little hard to see with my animation, we end up with the answer LL, FFFF, LLL, LL in this case. Okay, so that is our answer. That is our decoding for this particular emission string. Okay, so that's the procedure. Is it a lot of work? Was that hard? Well, that bears a little bit of thought. Obviously, we have to fill in a matrix. So the amount of work we do seems like it ought to be proportional to the size of the matrix. And so let's step out of the occasionally dishonest casino example and think more generally. If there's some state space, capital Q, right? This is how many different possible states our system could be in. Well, then that's the number of rows for the dynamic programming matrix. So the vertical dimension of this matrix, the number of rows, is size of Q. Whatever emission string we're considering has some length, let's call it n, and that's the number of columns we have to consider. So for sure, the number of elements we have to fill in this matrix is n times size of Q elements. But how much work is it to fill in one of those elements? Well, that is proportional to the size of Q as well, because in order to fill in a single element, as the arrows in this picture are kind of implying, We have to take a maximum over size of q terms, right? Because we have size of q possible previous states we could have been in, so that maximum is over size of q things, right? So we've got to multiply in another factor of size of q such that the overall time required for Viterbi is big O of n times size of q squared. The actual traceback step, by the way, is easier than this. It's just n steps, so that's not a big deal, assuming that we kept little recordings of exactly exactly which term won the maximum for each cell of the matrix. Performing the traceback is not hard. It's just n steps. So what dominates the time for Viterbi is the step that fills in the probabilities and the backtrace arrows for each of the cells. That is big O of n times size of q squared time. Just to round out this kind of time and space discussion, let's think about space now. And so for a hidden Markov model, how many numbers do we actually need to store? Like, what are the numbers that fully characterize the hidden Markov model? Well, we know it's the transition matrix, the emission matrix, and the initial probability matrix. That's size of q squared elements for the transition matrix, size of q times size of sigma for the emission matrix, size of q for the initial probability matrix. So that's kind of the sum total of all we need in order to have an HMM and do Viterbi with respect to that HMM.